Hello, welcome to a video on section 5.3 parts 1 and 2. So this is a video that most likely you are watching during class while I'm away for Kairos. And of course, if you're not in class, you could watch this whenever you get a chance. Okay, so obviously this is going to extend from the lesson we had in section 5.2 where we talked about the definite integral and related it to the area between the x-axis, or between the curve and the x-axis. So we had defined something called a Riemann sum, which involves sigma notation, and set it equal to something that looked like this, where this is what we call the definite integral. And again, what it indicates, or what it gives us, is a number that represents the area between the curve and the x-axis in between A and B. So, for example, here's a curve we have, f of x, here's A, here's B, and if I were to shade this area, that area is given by that expression. So the definite integral represents the area between the curve and the x-axis in between A and B. Now we're going to talk about some properties of definite integrals. That's kind of like what we did with limits a while ago. It's always going to talk about the properties of the stuff. So what if I reverse the order? Because A happens to be the left bound and B happens to be the right bound. But if I reverse the order, not a problem. Just put a negative to the left and we'll have equivalent expressions. So that's one property that's good to know. If you reverse the order, that happens. If it so happens that your lower and upper limits are the same, then there's no area, right? You're not sweeping any area from left to right, because the left and right bounds are identical. So in that case, the value of your definite integral will be 0. What if I have a constant multiple? If I'm multiplying some constant to my function when I'm evaluating a definite integral, I could put the constant to the left of the definite integral and they'll still be the same. So in this case, I just focus on find the area between f of x and the x-axis between a and b, and then multiply by k afterwards. Additionally, if k were negative 1, like we see right here, I just could put the negative to the left of the definite integral, like that. Not a problem. Going back to the constant multiple rule again. So here's f of x, right? And find my area. And if I double f of x, that doesn't quite look like it stretched. It looks a little bit different, but just, kind of go with it. Then you can see that we're adding on the same area right on top of it, so you're doubling the area. So it's kind of like a vertical stretch, but we double the area by doing a constant multiple, like we see in property 3 here. What if you're adding two functions, and you take a definite integral of them, both the same lower and upper limits? Well, you can just separate the two like this, not a problem. So you can find the area of each function individually and add up the areas. Or what if they don't have the same lower and upper limits exactly, but the upper limit of one function is the lower limit of the other function, where the first, actually let me change that color there. Let's go blue. So this is my first area, and then that'd be my second area, right? So this, of course, is that area, and that, of course, is this area. So I could just actually combine the two and just say, oh, I'm integrating from A to C. So it's called additivity because they link up at B. Another one that's kind of good to know is the max-min inequality. Here's how this one works. So, kind of curious how this relates to a typical definite integral from a to b of f of x times dx, which again is the area. Well, max f is the highest y value, right? Which of course happens right at that point. Min f, of course, is the lowest y value. Which of course happens at that point. And of course, here's the x-axis. So, of course, the area from, the definite integral from a to b of fx times dx is going to look all like this, right? What I do know for sure, which sometimes can be helpful, is that if I took the area of the rectangle, b minus a, here's b, here's a, and multiply it by the minimum f value, I'm just getting this area right here that I'm shading in yellow. That's of course going to be less than the definite integral, because the area of the definite integral is obviously going to be higher. We see the green area is higher than the yellow area. So if I took the area of this rectangle, which I'm tracing right now, which is defined by b minus a, of course, the width of the interval, times the minimum y value, that rectangle will have a lower area than the true area for the curve between the curve. It's the true area between the curve and the x-axis, which is shaded in green, or the definite integral. Or the definite integral will be less than area when I combine the maximum f value or the maximum y value with b minus a. So all this I'm shading in turquoise or light blue. The area of that rectangle, of course, is going to be greater than the area of the definite integral. So if we know the lowest and high y values for our curve and multiply by b minus a, we know that our true area between the curve and the x-axis will be in between those two. And then lastly, for number 7, let's say f of x is always above g of x. So say here's f of x. And here's g of x, not really great looking curves. Then we know for a fact that the integral of f of x from a to b is always going to be greater than or equal to the area of g of x between a and b, given that f of x is greater than or equal to g of x, because the area between the curve and the x-axis for f of x will be more than the area between the curve and the x-axis for g of x. So we call this dominance. So let's do some examples using the stuff we just talked about. So here I give you 3 definite integrals, 2 involving f of x, 1 involving g of x, and I don't give you any specific functions or any graphs, but if we just use the properties above, we should be okay. Like this case, we see that I can use property 1, which is just reversing the order of integration. So that's just going to be the negative from -2 to 3 of g of x times d of x. So that's just going to be -2. Now this one's kind of interesting for part B. Of course, it's going to be that if I reverse the order. I don't have -2 to 7, but I do see that these two integrals link up at 3, with a lower limit of -2 for the first one, upper limit of 7 for the other one. So I could think of it just like this. And don't forget, we still have that negative to the left. Actually, almost forgot that. Put a bracket. So, ooh, interesting. So we know that the integral from -2 to 7 is the same from -2 to 3 and from 3 to 7. So of course the negative outside the bracket, that's 10 plus -6, you get -4 for that one. Let's look at example 3, or sorry, example 1 part C. What if I have something like this here? Well, I'm going to break it up. Like this. Excuse me. So not a problem. Oops, forgot the dx. Don't forget to write the dx. That's your differential. And I could put the 2 to the left. And the 5 to the left of this as well. Okay. So I already know the integral from -2 to 3 for f of x is 10 and for g of x is 2. So that's just going to be 2 times 2 here. And, sorry, 2 times 10. And 5 times 2, which is going to be 10 altogether. So again, the value of the definite integral from -2 to 3 for f of x times dx is 10. For g of x is 2. Work it out, you get 10. Okay, let's look at D. So you're going from -4 to 6. Well, I don't see a -4 here, and I don't see a 6 for my limits. And even though -4 and 6 are double the lower and upper limits for this one right here, we have a problem because I don't know how fx is going to behave. Just because you double the limits doesn't mean it's going to double the area, because there's so many funky things that can happen from -4 to 6. And the curve can like do all this like wacky stuff. Okay, that's really wacky, but just because you increase the limits twofold doesn't mean it's going to double the area. It could actually even reduce the area. So we really don't know. Okay, here, again, I could separate. So 3 to 7, f of x times dx, plus 3 to 7, g of x times dx. And I do know the first one, so we did, actually it's given to us, it's -6. But I got no clue about the other one, because it was not defined for us. Only defined for -2 to 3 for g of x. So again, not enough info. Not enough information. Sorry I didn't write that for part D, the info part. Let's look at F. So we can wrap up example 1. So say we're told we're given another definition for g of x, but this time from -2 to 1. You have to find it from 1 to 3. Well, we do know it from -2 to 3, right? And since I know from -2 to 3, using property 5, additivity, right? Since I know from -2 to 3, clearly I know from -2 to 1 and from 1 to 3. And -2 to 3 we knew is 2, and -2 to 1 is -1. So now I could solve for the definite integral from 1 to 3 for g of x times dx, which actually will just be 3. So that's what happens there. Okay. Let's take a look at example 2, and you're asked to show the definite integral from 0 to 3 of root x plus 4 times dx lies between 6 and 3 root 7. How do we do that? We're going to use property 6 from page 1 of the notes. Sorry, yeah, actually it is property 6. So root x plus 4, you guys should know how that looks. You know, we've done that many times. Starts at -4 on the x-axis. When x is 0, y is going to be 2. If you feel so inclined, when x is 5, and then y is going to be 3. Just, you know, working it out. But I'm really just interested in looking at this from 0 to 3. Really just interested in this area. That's all. Well, again, we're asked to show the definite integral is between 6 and 3 root 7. Well, if I look at this rectangle, which is going to be the minimum y value for root x plus 4. So for y equals root x plus 4, the lowest y value in this domain is 2. But that happens at x equals 0. So that's using, again, property 6, where you take the minimum y value and multiply to the width of the interval, b minus a times min f. So of course that's going to be 3 minus 0 times 2. So that rectangle is clearly less than the blue shaded area, which is representing our definite integral for root x plus 4 from 0 to 3. And the highest y value in that same domain is going to be 3 root 7. Sorry, is going to be root 7, because you plug in 3 for x, you get y equals root 7 for y equals root x plus 4. And so, and the width of the interval is still 3. And that essentially proves that our the value of our definite integral has to lie between 6 and 3 root 7. If I shade another rectangle like that. So, and another way we can kind of look at it is we could use extreme value theorem, because it is a continuous function and we are in a closed domain. And we can evaluate f of 0, evaluate f of 3, and then try to find a critical point. Since f of x is root x plus 4, take the derivative, which is we've done before, and then finding a critical point and testing it out. But, I don't know. We don't need to go through all that trouble. Actually, yeah, that would justify that the lowest y value is going to be at x equals 0 and the highest at x equals 3, but we'll just do this. So don't worry about the EVT stuff I just talked about. We'll just move on to part 2. So average value of a function on an interval. So remember we did find average rate of change, right? That was find the slope of the secant line. So we want to do something kind of similar but a little different, the average value of a function. So in other words, we're trying to find the average y value. So say we have a curve that does this, right? There's a lot of different y values from A to B. Like say, this is x equals 1, say it's like x equals like 4. And so there's, obviously an infinite number of y values, but it's contained between the lowest y value and the highest y value. What is the average y value? If you had to pick all these different points on the curve and averaged all the y values for all those points, what would that be? So this is what we're doing here. And so again, the problem is infinite many y values to add an infinite number of x values in our interval. So let's start with a more finite case. Let's say delta x is b minus a over n. So the width of your interval divided by n, the number of intervals you're going to make, because you have n equal subintervals. And if I reverse things, 1 over n is going to be delta x over b minus a, just a little algebraic manipulation from this over here. Just divide both sides by b minus a, you get that. And if x equals c sub k, so c sub k is just going to be an x coordinate in a subinterval. Remember subintervals, here's a curve, here's A, here's B, and we make all these intervals. I'm actually drawing these rectangles, but if I make all these intervals, CK is just going to be an x coordinate within any particular subinterval. And of course, f of CK will be the y value that corresponds with it. So what if I averaged all the y values, or not all, but like a certain number of y values in my interval from A to B. So f of C1 could be the first y value, like right here. F of C2 could be another y value. F of C3 could be another y value, until I get to the last y value that I'm defining for my nth interval. And of course, all those y values divided by n, because that's the number of intervals I have. Using a little bit of nifty algebra, plus dot 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 times 1 over n. And we know 1 over n, okay, I'm getting lazy, just going to repeat that. 1 over n is delta x over b minus a. And I can kind of move that over here. Okay, I'm getting lazy, I don't want to write that whole bracket stuff. We kind of see that we're really just getting a Riemann sum, which we talked about in section 5.2. Now, what if I assume that n's approaching infinity? We have an infinite amount of intervals, right? So we make basically our intervals super thin. Well, in this case, if I'm taking the limit as n approaches infinity of 1 over b minus a times the sigma notation k equals 1, and f of ck times delta x that essentially just gets me, and I could of course move the 1 over b minus a to the left of that limit. Well, that's the definite integral, right? That's how we define the definite integral when you have infinite amount of rectangles and approaching infinity. So your intervals are, number of intervals are infinite, but they're super thin. So that's basically just going to be 1 over b minus a times the integral from a to b of f of x times dx. So this right here is what we consider the average value. It's basically the integral divided by, the definite integral divided by b minus a. So that's basically what we get, just right there. So let's do an example that deals with that, and then I can end this video and you guys can do some work in class. So use a calculator to find the average value. So we've talked about this in the calculator. Let me pull up the calculator app, which is right here. Might be a little hard to see, but alpha window, option 4. And if I'm going from 0 to 9, and by the way, I do want to insert the fraction 1 over b minus a. You can actually insert fractions if you go, I think alpha y equals, yeah, there we go. So 1 over 9 minus 0. So as alpha y equals how you can x fraction, and I had to insert it first. So I had to hit second delete to insert it to the left of the definite integral, or you could just clear and do it over again. Or you could divide by 9 afterwards. Just do definite integral first, divide by 9 afterwards. Totally fine. I know some people are probably asking, what, can I do that? Of course you can, not a problem. 3 minus root x and I think that is it. Takes a little while because it's kind of thinking. So it says it's about 0.9999, which is really just 1. So in the calculator for part A, we do 1 over 9 minus 0, definite from 0 to 9, of 3 minus root x times dx. And I have to put the 3 minus root x in parentheses so it stays protected. We get 0.99999, well, whatever, really just 1. And then part B is asking, will there be a value of x in that interval such that fx equals the average value? If so, find it. So the answer is yes. Our function is continuous. We're able to integrate it. So, and if we were to look at the graph of 3 minus root x, I mean, we didn't have to graph it, but if I did, it would look something kind of like this. X is 0, y is 3. And when x is 1, I know y is 2. And I think x would have to be 9 to get back to 0. So it's kind of like this. And of course, the definite integral is a shaded area between the curve and the x-axis. But will there be a value of x in our interval from 0 to 9 such that our y value equals average value? Well, y equals 1. Of course, is right here. Well, of course, y is going to equal 1 somewhere. But where does that happen? So simply just set 1 equal to our curve, right? Kind of move things around a little bit. Root x equals 2, so x equals 4. So it happens at x equals 4. So I just simply set our average value, which is 1, to f of x, which is 3 minus root x. So there's really no algebra there. I mean, no calculus there, just simple algebra. And of course, that is going to be where the average value happens at x equals 4. So that concludes the video. Uh, next time class meets, you guys will see a video on part 3 and part 4 of the section 5.3 notes. And that's it. Okay, have a great day, be nice to your sub, and go Warriors. Okay, bye.